Okay, so in this problem, we're asked to calculate the final temperature of a mixture. And let's go ahead and read through the problem and see what information we have. So we have a 2.85 gram lead weight. It's initially at 10.3 degrees Celsius. It's submerged in water, 7.55 grams of water at 52.3 degrees Celsius in a well-insulated container. So we need to calculate the final temperature. So when you think about an MCAT equation, all right, Q is equal to mc delta T, right? You know the different components that you need to know. Normally when we're doing these calculations, we do T final minus T initial. We need a specific heat for the material and we need a mass. And what you can see in this problem is you have the mass, right? The specific heat we'll have to look up. And then we don't have all of delta T because we have the initial temperature, right? And then we won't have the final temperature. So let's go ahead and set this problem up and see how you solve for the final temperature. So to begin with, we have to use our statement of conservation of energy, and we're going to say the Q for the lead, I'll just say L, plus Q for the water equals 0. And I can say that because in most of these problems, when it says a well-insulated container, that means there's no other heat sources. And that, again, gets us back to our statement of conservation energy that we've used before, is that the Q of the lead is equal to negative the Q of the water. Okay, so let's go ahead and write out what we know. I know the Q for the lead is going to be the mass of the lead, and that's this, right, times the C for the lead. Now, the heat capacity of lead, if you remember from earlier, or specific heat for the lead, sorry, is 0.128 joules per gram degree Celsius, and the specific heat for the water is 4.184 joules per gram degree Celsius. So I have both of these values. These values are known. And then I have T final minus T initial. Now, T initial is 10.3, so I actually have that value as well. Now, the Q, so the only part I don't know is this one, right? And so then I can say Q for the water is equal to the mass of the water times C for the water. And again, I have the mass of the water and I have the C for the water. And it's times delta T, so that's T final minus T initial. And you'll notice that I'm given the initial temperature of water. So what I'm going to do to sort of make this less confusing, I'm going to call this T for the lead that'll be the initial temperature of the lead, and this is going to be the initial temperature for the water. And what I'm trying to solve for is T final in both equations. So how do I do that, right? So what you're going to end up having to do is you have to take and go ahead and you can substitute these expressions in here into either equation really and solve for T final. So what I'm going to do is I'm going to use the equation on the left, and I'm just going to write in mass of lead, C of lead. So that's what I'm doing is I'm writing this term down, right? Times T final minus T for the lead, that's its initial temperature, plus, and then, all right, and then I'll be placing the second half of the equation, which is this one here. So that'll be the mass of the water times the C for the water times T final minus TW, which is the initial temperature of the water. Now all this is equal to 0. And what I need to do is then distribute, because when you have an equation like this and the variables are in two different expressions, you need to distribute and then isolate the TF parts of the equation and then bring everything else onto the other side and then isolate TF by dividing through by whatever constants are along with TF. Okay, so I'm going to go ahead and distribute. So MLCL TF minus MLCL TL, like that. And then that's going to be plus MWCW TF. And again, thermal equilibrium, right? So same temperature, don't need a different symbol. Minus, and then it's going to be MWCW TW, like that. And that's still all equal to 0. Now the terms I need to group will be the ones with the TFs, and then everything else I'll take to the other side of the equation. So now I have my TF terms. I'm going to bring them to the left. I'm going to say MLCL and that's going to be plus because I have a positive here, right? So that's M M of W, C of W, TF. And then I have all these terms here. It's going to be minus MLCLTL. So I'm just organizing it so I can rearrange it a little bit more easily. And it's going to be minus MWCWTW, like that. So you notice that these terms here are all known. It's the mass of the water, mass of the lead, the specific heat of the lead, and the temperature, initial temperature of the lead. And it's the mass of water, the specific heat of the water, and the temperature initial of the water. And the unknown, TF, is over here. So what I'm going to do is I'll bring both of these to the other side of the equation, and then I'll solve that over on the other on the next slide. So I've copied that over, and this is equal to 0. And then what I can do is I'm going to factor out TF. So I'm going to say TF is MLCL plus MWCW. And then I'm going to bring both of these terms to the other side. So I'll add them to both sides, and I'll just end up with ML, CL, and TL plus MW, CW, and TW, like this. Now, to get TF by its side, I need to divide both sides through by this term here. So then I'll have TF is equal to MLCL TL plus MWCW TW, and that's divided by MLCL plus MWCW, like that. Now, we can take all the numbers that we have from the previous slide and plug those in, and then we can solve the equation. So I will attempt to get that on here, but I don't know if I can actually fit it in here, so let's see what happens. Okay, so the mass of lead, or actually what I'll do is I'll go ahead and fit it all in here, and I'll pause the video and do that, and you can start it, and then you can see it, and then it won't be quite so messy. I can clean it up if I screw it up. Okay, so here's the solution worked out on the slide, and it's a little messy, I have to admit. But I was able to squeeze it all in by just moving all this to the left. But really, the calculation itself, setting it up, is not that difficult. The concept, right, comes back from here. Really, all you're doing is taking the two Q terms, right, and adding them together, setting them equal to 0. And then the rest of it is all algebra. And I know it's a lot of algebra, right, but it's actually not that hard to do. It just takes a lot of time. So again, this is the algebraic step. I factored out to get T final. That's the thing I'm looking for, right? And then I divided through by the terms that were with it. That allowed me to identify T final as equaling this term here, and then I just plugged all the numbers in, right? And then I simplified it down one step at a time and then added things together. So I got this, and then I just divided, and the units did work out. You're dividing joules by joules per degree Celsius, so you end up with degrees Celsius. So this is the final temperature. It's not very much cooler than the original temperature of the water because the specific heat of water is so high. And so it just drops a small amount because the lead doesn't really have a large heat capacity, so it warms up very easily, and the water temperature drops only by a half a degree or so. Okay. Now, having said that this is how you do this problem, right, there are other ways to solve these problems, and I'll just show you. I've pointed out a couple of times, I believe, the program Wolfram Alpha. I just typed in the original equation. This is this equation typed in with all the variables inserted, right? So mass of lead, specific heat of lead. So when you look at that, it's the mass of lead, the specific heat of lead. Oh, I have an extra 8 in there, so I get rid of that. I just double clicked on it, I think, when I typed it. 4.184, there's an extra 8 in there. My keyboard's a little weird. And I hit enter like this. And it'll solve for the value of x for you. And 51.82, which is exactly the answer I believe I got down here doing it the old-fashioned way. Now, I would say it's okay to do that to check your work, but you need to make sure that you can do this kind of work on your own. It's a kind of skill that you need as you move on through science, is how to set up equations that need to be solved. And then ultimately, as you move into a profession, this kind of stuff can often be done on a computer. But there is actually some satisfaction in being able to still do this kind of work. So this is actually a little bit more practical application kind of calculation, more like an engineering calculation. And I've done it on something that I think everybody's familiar with. I have a 6-pack of sodas, and they're at 25 degrees Celsius, so roughly room temperature. And you put it into an ice chest, and assuming each soda has a mass of 0.35 kilograms and a specific heat capacity of 3,800 joules per kilogram, so it's not the specific heat in the same units that you're used to, but it's per kilogram, degrees Celsius. How many kilograms of ice do you need to cool the sodas to 0 degrees Celsius? And the heat of fusion of ice is 6.01 kilojoules per mole. So this is the heat that's absorbed as H2O solid is converted into H2O liquid. Okay, so that's what we mean by heat of fusion. They call it fusion because the ice crystals, as they melt, like the ice cubes, look like they're fusing together because the liquid sort of sticks them together. Okay. So let's look at this problem and what we have to do. It says a 6-pack of soda. I want to start at 25 and I need to get to 0 degrees Celsius. So this is an MCAT kind of a calculation. So I'm going to say T final, or sorry, Q is MC delta T. And then I have my mass. It's 0.35 kilograms. I have a specific heat of 3,800 joules per kilogram degrees Celsius. And then I have my delta T, which is my T final minus my T initial. So T final is 0 degrees Celsius, and T initial is 25 degrees Celsius, like this. Okay, so you notice that I have everything I need here to calculate the energy needed to cool the sodas down, right? Sorry, to cool one soda down to 0 degrees Celsius. Now I have 6 of them, so conservation energy would say once I get this number, I'll just multiply it by 6, and that's how much energy it will take to cool 6 sodas down. Okay, and if you want to do 12, you could also do 12 sodas and stuff like that. So I did it per soda because it's kind of a more flexible number. And by the way, these are not completely random numbers. I think I, again, got them off Slater's site or somebody's problem engineering class I think had to do or something. So anyways, I stole the numbers off there, but this is my own problem. Okay, so let's go ahead and calculate the heat to cool one soda. So Q is equal to 0.35 kilograms. Now I didn't convert it to grams because this is not in grams, right? And so it's going to be 3,800 joules per gram degrees Celsius. And my delta T is minus 25 degrees Celsius. So that's going to give me minus 33,250 joules. And now that's per soda, right? So I have 6 sodas. So you could scale this to a 12-pack if you wanted to. 6 sodas times 33,250 joules negative per soda. So that'll cancel. And then that leaves me with minus 199,500 joules. So it's quite a bit of energy. Okay, so let me convert this number into kilojoules, and I'll explain to you why I'm doing that in a second. So there's 1,000 joules per kilojoule, and so that gives me 199.5 kilojoules to cool down that 6-pack. Now, this is the kilojoules per mole of ice. Oh, sorry, negative. And so one of the things you have to think about is I have kilojoules of energy that I need. Oh, I can't get my mouse over here. Hang on. It's not showing up on the screen. I don't know why my mouse wouldn't show up on the screen for some reason. So it's 6.01 kilojoules per mole for ice to melt. And then I need this much energy in order to cool the sodas down. Now, the Q for the soda is opposite the Q for the ice. That's the conservation of energy statement that we've been saying before. So the Q of the ice for melting the ice is actually 199.5 kilojoules. And this is for the ice melting. And now what I'll do is I'll convert that into moles of ice. And so it's 6.01 kilojoules for every 1 mole. And then it's 18.02 grams of soda for every 1 mole of soda. Or of water, sorry, for the ice. And then I'm going to need that in kilograms, so it's going to be, again, 10 to the third grams is a kilogram like this. And that comes out to about 0.6 kilograms. Oops, 0.60 kilograms of ice. Okay. So in terms of pounds, that's about 1.3 pounds of ice, and you can do that conversion on your own. But so think about that. That's just for 6 sodas, right? And that's to cool it down. And that's kind of the problem, like when you have try to put 20 sodas in an ice chest, and you know how all the ice melts. It works much better actually if you put the sodas in the fridge and you cool them down first, and then when you stick them in the ice chest and you throw the ice on top of it, the ice doesn't melt. So that's like an old man trick right there. All right. Anyways, just following through what we did on this problem, right? First thing we did is we calculated the energy we needed for 1 soda. Then we calculated the energy for all the sodas in kilojoules, and the reason I use kilojoules is because my heat of fusion, the energy required to melt the ice, is in kilojoules. And then my problem-solving map was really kilojoules to moles of ice, to grams of ice, to kilograms of ice, and then in my head, I just did it on the calculator, it's 1.3 pounds of ice that you need, but it only asks for the mass of ice in kilograms. So there you go. If you did more sodas again, like two 6-packs, it would take right, 2.6 pounds, and you know how you get a 5-pound bag, that would be like for 2 12 packs, that kind of thing.